Good morning. I want to take a few minutes and talk about why a certain type of lightning arrestor or surge arrestor fails. This week we had a trouble call, had a tap fuse that wouldn't stay in, and the men that were working that call found the cause to be this arrestor. Now, they did a great job because they were able to see the burn marks that were on the bottom and the swell up on the top of this. Normally this would be concave, and you can see that there was a pressure inside, probably caused that flash on the bottom and then caused the front to pop out. This one hasn't burned up yet, but usually when they start arcing on the inside, you'll watch it burn a hole from the inside out. This one isn't that far along yet. So what we're going to do is we're going to take this one apart. We're going to disassemble this one, and I'll show you why this arrestor fails. Now, the first thing we're going to do is we're going to put on our PPE, because the most important thing here, what comes first with testing like this? Safety. So we have some good gloves, cut resistance gloves that we're going to use. I've already prepped the front of this so that the end cap will come off easier. When these were manufactured in the 90s, they took the glass tube, they put the guts in, and then they crimped these two caps on, and they have rubber gaskets. After 15 or 20 years, the rubber gaskets start to suffer. We're in central Texas. We'll go from 20, 30 degrees in the winter to 105 degrees in the summer. So these drastic temperature changes affect these rubber gaskets. Once the rubber gaskets allow for moisture ingress, there's now moisture defeating the insulation properties of the arrestor on the inside of the tube. So we're going to pop this front end off. And hopefully it'll come off easily. Okay, so now we have the end cap ready to come off. Now there's a spring down here that loads this arrestor, the internal guts, the metal oxide varistor blocks, and all the gaps and all the springs, everything is loaded between this cap and this cap under tension. So we're going to pop this cap off, try to keep stuff from flying out at us. And what we can see here, this is the rubber gasket right here. So this gasket, the manufacturer thought would last forever. He does a good job in this area at about 15, 20 years. I told you this arrestor is a 1997, and it was the only arrestor that we used from 1992 to 2002 when we started using polymer arrestors. So we probably had thousands upon thousands of these installed, and now we're going to spend years and years taking them off the line as they begin to fail. We can usually hear the early stages when these arcs start to go inside this contaminated tube with radio frequency interference. This one I didn't find before it failed. So this one had enough going through it, and it was a dead short, wouldn't hold 250 volts. Every time they closed the primary tap fuse, it'd blow back. They were able to find this arrestor. Now we'll show you what happened. So we're going to dump the contents out of the tube. Oh, maybe I can keep them vertical. So there's the spring that I told you was at the end. Here's the spacer that the manufacturer gives us, aluminum, so that we can have this length of tube. These are the blocks, little ceramic blocks, and then you can see where the arcing went through. These make little gaps. So they're stacked up here just like this. They're added to the aluminum tube, and then here are your 4 metal oxide barrister blocks. These are amazing. They have a resistance until they reach their rated voltage, and 4 of these in series are not supposed to leak until they get to 15,000 volts. I think on the end cap, we have the information where we get the date, we get the manufacturer's name, and we show that maximum continuous operating voltage is 15.3 kV. So above 15.3, we expect to start seeing a current flow through these MOV blocks. And when the current gets high enough and these shunt and actually become zero resistance, the overcurrent protection device will operate, the voltage will fall to zero, and by design, these blocks are supposed to regain their resistance. That's how the over voltage from the lightning or surge would reduce the resistance in the MOV blocks. They go dead. When they go dead, the resistance returns and the over voltage is gone. The MOV is back in service. Now this is a common problem for us now, but this probably had water in it through those gaskets. The inside of the tube doesn't have any skirts. The moisture defeats the insulation value. We get a short circuit from one end to the other. The ground was connected to here, the system neutral. The hot lead was connected to here. We get a short circuit, overcurrent operates, but it's still full of moisture, and the MOV blocks are probably destroyed. We can't keep the line on until our guys find the bad arrestor. So we've been talking about this for many years. We try to find them before they fail with noise, and I wanted to take a few minutes and show you the internals. A lot of times when I find them with noise and they have not failed, all these metal parts will be rusty. Here you can see this high current pass through and flashed all of this. All right, well, I appreciate it.